Hi everyone, Mrs. Bilo here. I'm continuing from where I left off in the last video. So again, John Dalton in the 1800s was working on this idea of atoms, that there has to be something like this small unit that makes up everything. And we're going to talk about how other scientists further refined this model until we get to present day with the most current model and understanding of atoms. All right, so moving on. So now we're looking at J.J. Thomson. So he discovered the electron. And again, we use this symbol. We use that to represent an electron. And he stated that electrons had a negative charge, which they do, and a positively charged cloud. So now we have this idea that, yes, there are other things that make up an atom that have positive charges and negative charges. We don't quite have the nucleus yet, or those electrons going around the nucleus, but we're getting there. We're making progress. And then there's no mention of neutrons in this at all. And again, he did not take into account for the nucleus. So again, this model has no nucleus, but we're getting there. So how did he figure this out? So he did a simple experiment with something called a cathode ray. And essentially, I actually have this somewhere in my classroom, like this thing. It just doesn't have, I think, anything inside of it. So when you, so you have this piece of glass here, and you can put 2 electrodes on either end, okay, and run basically a beam of particles flowing inside of this glass sealed tube. So you can see right there, that's the beam of particles. And so this is electricity, which is, electricity is just electrons moving. That's why it's called electricity. And then what he did was he put a magnet near this to see what would happen. So this beam of particles, which is electrons, that's what electricity is. It's moving electrons. When he put a magnet close to it, so the cathode ray beam of particles was deflected away from the positive charge. Okay. I'm sorry. Oh, reflected away from the, oh my gosh, the negative charge. And the beam was pulled towards the positive charge. Okay. So if you have like something has a positive, negative, right? Opposites attract and like charges repel. So this cathode ray, so again, this is made up of electrons that are flowing. They would bend towards the positive plate. So something has a positive charge, which makes sense because opposite charges attract. Versus like charges, so the electrons, okay, have a negative charge, would repel from another negative charge. And so he concluded that the cathode ray, the beam of particles, was composed of negatively charged particles, which are electrons. And he also determined that the mass to charge ratio of the beam of particles were smaller than any atom. So he was saying that this beam of particles, when he was taking that into account, was less than the mass of atoms. So therefore, this beam of particles is smaller than an atom, and therefore must be some component then in atoms. So this led him to conclude that that negatively charged particle must exist as part of the atom. But he also knew that, generally speaking, atoms overall had a neutral charge. And so he's like, well, if there's this negative charge that's a component of the atoms, then there must be some type of positive component to cancel that out. And thus we have this is called the plum pudding model, because I guess that's like a dessert and it kind of looks like that, where we have these electrons that have this negative charge, but they're in this cloud of that's positively charged because overall atoms have to be neutral. But they contain smaller particles, the electrons, that have a negative charge. So we're getting there. We're making progress. Next, we have Rutherford, who determined that that positive charge is actually located at the center of the atom, and these electrons are around that, or they must be around it. So this is like a pretty popular, I literally have a pin of this on my lanyard. This is a very popular model of the atom, but it's not the most current one. Now, Rutherford discovered the nucleus while doing what's called his gold foil experiment. He, however, isn't explaining for the electron orbiting the nucleus. So he just said it was kind of like this random pattern of the electrons going around the nucleus. So this gold foil experiment, what is it? Okay, so he had these alpha particles, which had a positive charge, were fired at a thin piece of gold foil, which is made up of atoms, right? Gold atoms. And most of these positive charges went right through. However, some bounced back. So when he was firing these atoms, the beam, so here we have these positively charges going through. Most of them just passed right through the gold foil. However, every once in a while, one of these positive charges would do one of these. Boom, boom. And therefore, when he did these calculations, he found that at the center, there must be something that has a positive charge. Remember, like charges repel, two positive charges are going to repel each other. So if he's firing something that has a positive charge and it's bouncing off of something, that something must also have a positive charge. And so he concluded that there must be something at the center of the atom that has mass and also has a positive charge. And that is what we call nucleus, which, yes, it does have a positive charge, and it does have mass. We also have neutrons present as well in the nucleus. However, we aren't quite explaining for the electrons that go around the nucleus. And then we get to our last two models. So this one right here, this is really, again, you see this a lot. It's called Bohr's model. I even showed it up here. It's not the most current model. It's the second most current one, I suppose. And we still use this for teaching the concept of atoms. So it wasn't totally wrong, but it wasn't totally right either. So he stated that electrons orbit the nucleus. And yes, they do go around the nucleus. That's true. However, when he showed it, it was this planetary model, almost like electrons orbiting, like how we as Earth, we orbit the sun. It was kind of that similar idea where these electrons are orbiting the nucleus and they're following like this fixed like path, so to speak, which is not true. This theory doesn't work for super large atoms. And again, this is commonly how we draw electrons, to get the point across. But note that electrons aren't like following this nice little neat path. They are in levels. That is true. There's the levels that are close to the nucleus, and then there's levels that are far from the nucleus. That's true. But they're not following this fixed pattern or fixed path of travel. And that's where our most recent model comes in, the quantum model, Schrodinger's model. And he stated that electrons are found in a cloud, which we're going to talk about next in chapter 4. We're going to talk about these clouds. So rather, electrons are in this area, but it's impossible to know their exact location at any time. We have a probability of where those electrons might be found, like, oh, there's a high probability the electron could be here or like here or here, but they're very fast moving and we don't know for sure where they are at any given time, but we know, oh, they must be in this space somewhere, which we call an electron cloud. So they're still around the nucleus. They do still exist in these levels, but they're not necessarily on this fixed path of travel where we can point them out. Rather, we could just say, hey, they're probably somewhere in that area. And though that is the history of the atom, again, this is our most current understanding, but we still use this one for teaching purposes, even though it is not the most current model.